Hi, my name is Keon Salehi, and this is my bridge design for Civil 2120. So the name of my bridge is All Reliable. The different materials I used were around 650 popsicle sticks, white Elmer's glue, and wire cutters to adjust the lengths of some of the popsicle sticks. The measurements of my bridge, so the length is around 630 millimeters, while the height is 230 millimeters. There's a clear span of 410 millimeters, and the height of the span is 100 millimeters. So the weight of the bridge, I did this by putting a glass slab on a scale and then zeroing it and then placing my bridge on top of the slab to make sure I get the full weight of the bridge. So once I did this, it was around 993 grams or around 1 kilo. So now let's get on to the actual looks and design of the bridge. So this is my actual bridge. It's pretty big. I don't know, I guess it's kind of small in terms of the size specifications, but so it consists of a upper deck. This is the upper deck. It has a clear place for cars. It's smooth, and these are the little guardrails on the side, and it's made up of 5 layers of cross-laminated popsicle sticks, so that it comes with, like, it's a really strong rigid surface. And then as we move down, we come to a additional layer of popsicle sticks here, and then we have our triangle support system. So how this works is it's a basic popsicle triangle bridge where it consists of popsicle sticks coming from each side, and then gluing them on the ends to create these little triangular support system that actually, I call this bridge All Reliable because this is one of the most classical bridge systems for popsicle sticks and general bridges, and it always seems to be the most effective, so that's why I used it. And as we get to the bottom, these are little parts to keep the sides of the thing together, the supports. So these are just additional supports, and then we have another system of cross-laminated timber or popsicle sticks here on the inside, where it keeps this top of the bridge attached to this column, and this column actually consists of about 25 popsicle sticks on each side. That is a really strong, actually surprisingly rigid column, and it's hollow on the inside, which makes it lighter, but saves me popsicle sticks. But yeah, we have around 3 or 4 layers of glue lam popsicle sticks, and I have additional supportive supports for these. So on the ends here, where you'll see some more stress coming from the angle, there's 3 popsicle sticks opposing to 1 here, and yeah, so it's just a combination, this bridge, of cross-laminated timber, glue lam, triangular support systems, and cross-laminated columns that really brings out the All Reliable classic bridge design for popsicle sticks, at least. So the reason I added all these different features to this timber was because I learned in Civil 2120 that there are multiple different methods of using younger pieces of timber and more sustainable pieces of timber, and using glue to make them more rigid and more structurally sound. I also use my prior knowledge of bridges, which is that when creating a bridge, you need to use shapes like arches or triangles to get a more, even load applied to the actual bridge. Since we're using popsicle sticks, I thought that arches won't be the most practical, so I decided to use triangles and triangular shapes instead. By combining that with other features like cross-laminated timber and glue-lam timber, we can actually create a very strong and structurally sound piece of, architecture or a bridge. So now let's get to the fun part, the compression testing. Before we get to the compression testing, we need to make a prediction on how our bridge is going to fail. So my personal prediction is that there's going to be a shear failure in the bridge right at this point. I'll show you. Right here is where this top half of the bridge plus the supports is connected to the sturdy columns. So here is around 2 to 3 layers of cross-laminated timber, and this acts as the method of holding this bridge together. So as we can see here, this support is attached to 5 popsicle sticks, and that is what keeps the entire top half of the bridge attached to the column support of the bridge. So my prediction is that there will be a shear failure here due to a lack of glue or maybe a lack of layers of timber, but I feel that these will break, causing the bridge to collapse. So I'm pretty confident in the performance of my bridge, so we're gonna start off strong with a 10-pound weight. Okay, so now we're gonna double it up to 20 pounds. So these are 10 pounds, so now we're gonna do 30 pounds. This is a 20-pound weight. So now we're gonna do 40 pounds. So now we're gonna do, I don't know, we're gonna try to load it up with all the weights. So these are all the weights we have. So our next test is gonna be me. So we used up all the weights that we have, and the bridge didn't budge. So we're gonna go a little bit more extreme. I'm about 150 pounds, so I'm gonna stand on it, see if it breaks. As you can see, my prediction was kind of right. There was shear failure here and here, right where I said the glue and the weak points were. And but also, I guess I loaded it too much and the entire support system failed. This side was fine. This side is actually still pretty attached, pretty strong, but this side did not fare so well. This is actually the side that I stepped on first, and I hadn't actually made both my feet onto the thing, so yeah, pretty disappointing, but the span is actually fully intact. It's, I honestly think if I added more supports, that it would have actually held me up, so stuff for the future. So now we're back upstairs. All reliable is broken, it's destroyed, the deed is done. So now we need to calculate our structural efficiency. So the mass of the bridge was around 1 kilogram, which we measured from earlier, and when I loaded myself onto there, I was around 150 pounds. And when we were using our actual calculated method of loading the bridge using weights, we reached a maximum weight of around 80 pounds. And using these values, like, since we don't have an actual ultimate load of failure, because I doubt it would have been able to reach 150 pounds. By the way it failed, it literally just disintegrated in a lot of parts. So what we could do is we could take our 150 pounds of my weight, which is when it was destroyed, and the 80 pounds which we loaded it to, which it seemed to be doing fine. So I added those two together, divided it by 2 to get 115 pounds, which is my estimated load at failure. So now we can use the structural efficiency formula, which is the load at failure over the dead load or the mass of the bridge. So it would be around 52.16 kilograms over 1 kilogram, which just brings us back with 52.16 kilograms. So our structural efficiency is around 52 kilograms. So that brings us to the end of our video. Really sad to see All Reliable go after all the hours I spent on it, but it's part of the craft, it's part of the assignment, so can't complain. My name's Keon Salehi, and this has been my Civil 2120 term project. Goodbye.